Alright, so this will be lecture 4, which is going to be about curves and the push forward. So let me begin by just saying a little bit about what is a curve. Now, when I think of a curve, I usually think of something, I guess I start in the plane. It could be anything really. It doesn't have to be a graph, right? I suppose you could think about curves which form loops, that have the same ending and starting point. I don't know, we're not getting into all that at the moment, but basically it's just some, you could say one-dimensional kind of subset. Now, and you could maybe lie a string along such a thing, right? And that would be a curve. Now, we're really interested in a slightly more technical definition, though. So we want to talk about what's called a smooth parametrized curve. And so what that in part entails is a mapping. Typically we've used alpha here in this this part of Gunnell or O'Neill, I forget which. Anyway, so alpha is some mapping from some interval, some connected subset of real numbers to, well, generally Rn. Of course, O'Neill is primarily interested in R3, but you could just as well define it to be Rn. Now, smooth, as the usual meaning, that means you can take as many derivatives with respect to the domain variables you like. Parametrized, well, that just speaks to the nature of the setup here. We have a mapping which goes from the reals to Rn. So in some sense you could think about that as like, taking the real line, right? And you got some time t, and then over here you got your copy of, well, it's kind of a funny looking Rn. Well, here's x1, I guess here's x2, here's x3, here's xn. I guess you could draw it that way if you're so inclined. Anyway, parametrized curve, just some kind of mapping that takes you from here over to there, right? And we call that mapping alpha. And we refer to the mapping as the curve, the parametrized curve. Now, sometimes I would say a curve, the actual point set in Rn, you might just call a curve. You might call alpha of I the curve, all right? Whereas the mapping alpha is the parametrized curve. All right. Again, smooth refers to the mapping. You could also talk about continuous curves or once differentiable curves. The reason we like to talk about smooth curves and not just a continuous curve is continuous curves have some kind of really strange things that can happen. For example, there are examples of what are called space-filling curves. It's possible to have a curve in alpha from I to, say, R2, from from the reals actually. There exists this example. So something like alpha just being continuous, okay, from the reals, and it ends up being, I think it did the unit square. And if you were to look at it, here's a picture of where the curve, the space-filling curve goes. It literally fills. It's hard to even imagine how that happens, but it does. There is such an example of a continuous curve. Oops, I think I probably bled through the next page. Oh well. And for example, there's a whole book on this by Hans Sagan, I think of the same title, Space-Filling Curves. Anyway, these are kind of obviously pathological examples. We'd like to avoid them. Smooth, on the other hand, is good. That gives us certain expectations about, well, let's see, what does that actually say? That would say that alpha prime of t exists, right? Which in some sense means that I'm being distracted at the moment by someone. All right, so that's not actually quite enough for what we want geometrically, because you could have, for example, it's smooth, right? And the derivative could just be 0. If I just had a mapping from R to Rn such that, you know, I mean, here's what I'm getting at. The other example that you don't really want would be this: alpha of t equals to, say, some point p, all right? A fixed point.
Have you made mistakes?
I have not made any mistakes yet, Daniel. I'm sorry. I'm sure I will make a mistake soon, and then you can have that paper, okay? All right.
Can I go outside?
Yeah, you can go outside and play. Thanks, Dan. So, this is obviously not what you want. I mean, here we have alpha prime of t is, well, 0 for all, not that I've defined that yet, but this turns out to be right. Turns out to be right for all t, right? So alpha smooth, but this is not a curve, right? I mean, this is a point. The parametrized curve, the image of it, the curve, if you will, is it's just a point. Well, that's not really a curve, right? So that brings us to, I think I've spent entirely too long getting to the point here. Oh, I'm sorry, getting past this point. Yeah, 6 minutes, my goodness. Seems like I've said nothing. All right, so definition, alpha from I, again, some connected subset of real numbers. I think O'Neill takes it to be open. Maybe kernel takes it to be open. Smooth and such that alpha prime of t is not equal to 0 for all t is called a regular curve. That's really what we want. Sometimes I'll call a regular curve a non-stop curve. It doesn't stop, all right, if you're thinking of it in terms of motion. Regular parametrized curve. Okay, so I'm trying to slap the parametrized on it. So we have a distinction in language between the point set and the you might call it a path. I sometimes call the parametrized curve the path, and I call the point set the curve. But anyway, there it is. Now, I have just used something I haven't defined yet, which is the velocity, right? So let's go ahead and define that. Definition for a parametrized curve, alpha, and t in the domain of alpha. And I guess I should say smooth. I want to assume that the derivative I'm about to write actually exists. I'm not assuming alpha has to be regular. I mean, alpha could be. It doesn't have to be regular. That's not necessary here. But t in the domain of alpha, we define. Sorry, I'll get to it eventually. Alpha prime of t equals to, here it is. It's d alpha 1 dt partial x1 at the point alpha of t, and plus plus d alpha n dt partial xn at alpha of t. So this makes the, so alpha prime of t is an element of the tangent space at alpha of t of Rn, all right? And so what this means then is that the velocity, and of course we'll call this, naturally we call this the velocity of alpha, right? So the velocity of alpha is what? It is an operator. It's an operator on functions, right? Defined near alpha of, let's see here, of I. I mean, if you have a function which is smooth and it has a domain which at least contains some open set surrounding the curve, certainly we can make these calculations. And just to remind you, alpha we can write as basically alpha 1, alpha 2, alpha n. I mean, maybe I'm not reminding you, maybe I'm just telling you. These would be the component functions. This is an element of Rn. So each one of these is a function of time. So each alpha 1 through alpha n are the component functions of alpha. Those are actually real valued functions of a real variable. All right. So let's look at an example. Let's look at an example here to get a sense of what does it mean. What does it mean for a velocity vector for the velocity of a curve to act on a function? Like, what is that? What's that about, right? So an example that I like is we could let alpha of t equal to, let's say, 1 over the square root of 2 cosine t sine t t. All right. Then if I have that, then the velocity alpha prime of t is going to be 1 over square root of 2. And I put that up front. I'm just going to keep that up front, right? And so the derivative of cosine is minus sine t. And so I get partial x. And then, let's see, I'm going to save I'm going to put the evaluation on the outside here. So plus cosine of t, partial y, you see what a second I mean here, plus partial z, because the derivative of t is just 1. Okay, all of that at alpha of t, all right? So you might notice that the reason I put the 1 over square root of 2 in there is just so that this guy will have this very nice property. The length of alpha prime of t, in other words, the speed with my 1 over square root of 2 factor is, okay, so it's sine squared plus cosine squared plus 1. In other words, it's the square root of 2 divided by square root of 2, so the speed is just 1. So that makes this, so this is actually, t you could actually take to be arc length, given my setup here, okay? Anyway, so there's your velocity operator. And now we can do things like, how about, let me do a different color here. What would, for example, alpha prime of t acting on the function z, what would that look like? Well, if you think about z hitting these operators, 0, 0, 1, right? So I get 1 over square root of 2 times 1. I guess the evaluation at alpha of t is kind of boring here. So you get 1 over square root of 2. All right. So apparently what that means is that the rate at which z is increasing in the direction in which the curve is progressing, right, is 1 over the square root of 2. Which makes a lot of sense here, because if you look at this, what this is a helix, right? And so this is a helix, and so if you look at the, it going up, the z is always increasing at that constant rate of t over the square root of 2. It makes good sense, all right? But this quantifies the rate of change along the whole curve of this given function z. So that's kind of an interesting new thing. We're not looking at a single directional derivative. We're actually able to look at a whole ensemble of them all along the curve. All right. Another thing you might look at, I think another interesting function here to check on would be alpha prime of t on, say, x squared plus y squared. All right. So that's going to give me, the derivative with respect to x is going to give me 2x. So I get like minus 2x sine t. And then this is going to give me 2y. So I've got like plus 2y cosine t. You're like, you forgot the 1 over square root of 2. I'm not done right. I'm not done right. Wait for me. It's down there. There it is. All right. And of course, c differentiates to 0, so that's not there. Now this time the evaluation is a little more exciting. Here we're going to put x equals to cosine t over square root of 2, y equals to sine t over square root of 2. And what do we get? Well, we get, let's see here, minus 2 cosine t sine t plus 2 sine t cosine t. And I got 2, so I got a 2 down here. Not that it really matters because these cancel and you get 0. Of course, this makes good sense because, as you may have realized, this this helix is winding around a cylinder, right? X squared plus y squared equals to 1/2, right? So we actually have x squared plus y squared equals to 1/2 true. right? This surface is a right circular cylinder, and alpha of t actually satisfies that equation, right? So that means that the curve is on the cylinder, and of course, in turn, this function x squared plus y squared is not changing; it's constant along the curve. Another example we could look at. I'm trying to get as much mileage as I can out of this one here. Let's see, another color. I wouldn't use orange yet. There we go. Alpha prime of t acting on, how about inverse tangent of y over x, right? So let's see here. Inverse tangent's a little bit of fun. So let's see here. Going back to the definition, remember, since we've probably forgot it by now, we got to do the derivative of the x component with respect to time times partial x and so forth. Oh, I'm sorry. What am I talking about? We already got that up here, right? So 1 over square root of 2 minus sine t. And, okay, derivative of inverse tangent, well, that's 1 over 1 plus y squared over x squared. Derivative of that with respect to x gives me a minus y over x squared, right? Okay, great. And then plus, I guess I need to close big parentheses. All right, plus cosine t, open my big parentheses, 1 over 1 plus y squared over x squared. And differentiate y over x with respect to y, I get 1 over x, right? Okay, great. And let's see here, close these guys. And, oh, I think I lost my, no, I didn't lose it, it's fine, it's fine. Okay, then if you look at this, we can put some stuff together. What we really got is multiply by x over x, right? And you get, let's see here, y sine t, right? Plus x cosine t, all divided by the square root of 2 times x squared plus y squared. All right, now that should all be evaluated at alpha of t, right? This should be evaluated at alpha of t. Evaluating at alpha of t means I set x equal to what it is and y equal to what it is on the curve. So x is actually cosine t over root 2, and y is sine t over root 2, so this gives me sine squared plus cosine squared divided by root 2. So I get, what do I get? Well, I get 1 over 1/2, and as I mentioned, x squared plus y squared is a half, so I feel like I have done something incorrect. Shnikes, where did I go wrong? Oh, duh. So the 1/2 is the x squared plus y squared, right? But then I also have a half upstairs. Scratch that. And then these cancel, and we get 1. Oh, you had a good sleep. Awesome. You can go outside and play? Okay. All right, so, and that also makes good sense, right? Because this is nothing more than our old friend theta, right? Staying away from where x equals 0. Right, that's the theta function. And basically this helix is wound at uniform, theta is increasing uniformly as you go up it. So it makes sense that the rate of change of theta along this helix would be 1. All right, so I have another example, if you'll bear with me here. 3. Example, I guess I should call this one. This is the example that matters. I'll call this example 1. And I'll call this example 2. So here we go. Alpha of t. This is sometimes called the twisted cubic. So we get alpha of t is t squared, t cubed. This is not arc length parametrized. And don't ask me what the arc length function is for this thing. I don't want to know. All right, alpha prime of t is, well, partial x plus 2t partial y plus 3t squared partial z. All right, all of that is evaluated at the point alpha of t, which by the way is t squared, t cubed. All right, great. And for kicks, we could look at how does alpha prime of t act on the function x to the sixth plus y cubed minus 2z squared. All right. Let's see, so how's that going to go? That's going to go 6x to the fifth plus 2t, all right. Derivative of this with respect to y gives me a 3y squared, and then minus, let's see here, derivative, minus a 3t squared. Just to be clear, this term is that term. This term is that term. And there is a 1 here, which I put here, although I didn't tell you until just now. All right, and then, so 3t squared, partial derivative with respect to z of minus 2z squared is nothing more than minus 4z. Great. Now all of this stuff is supposed to be evaluated at x equals to t, y equals to t squared, z equals to t cubed. So what do we get? Well, we get 6t to the fifth plus 6t times, well, y squared is t to the fourth, right? And let's see, minus, oh man, why do I have a, I put in an extra minus there, oops. This was supposed to be plus right there, sorry about that. So minus 12 t squared, z was t cubed. So I've got a t to the fifth, a t to the fifth, a t to the fifth. 6 plus 6 is 12, 12 minus 12 is 0. Aha, well why is this? Well, I think I'm kind of, it's a little bit of a preachy example, but essentially the point is this. If you look at the curve, well, the surface rather, x to the sixth plus y cubed minus 2z cubed. Don't ask me what that looks like, but it is a surface in R3, right? This represents some surface in R3, and the curve in you know alpha of R is a subset of that surface. Let me call that surface S. All right. I mean, if you like, S is the inverse image of 0 of this level function over here. So of course we find that alpha prime, the velocity doesn't, this function doesn't change along the curve, right? Because this curve, alpha of t, actually lies on the level set of that function, which by the way is a surface in R3. That was analogous to that x squared plus y squared thing I did for the helix in the last example. All right, moving on here. So we can also talk about reparametrizations of a curve. So definition, we say h, a smooth function from j to I, is a let's see here, reparametrization. Well, I guess we don't quite say that. We don't say that that's the reparametrization. We actually say that, no, I guess we do. The reparametrization, I'll make up my mind here eventually. Alpha, let's say a smooth curve which has domain I, all right, is the reparametrization of the parametrized curve. And again, I'm assuming smooth. Sometimes I forget to say it, but parametrized smooth curve alpha. And beta, all right, in particular beta is, it goes from J to Rn, all right, where particularly we define beta to be equal to alpha composed with H, is the reparametrization of alpha by H. Often we choose H so that it changes, say, alpha to be arc length or something, right? So in principle, don't ask me to calculate it, but you could do such a thing with example 2, you could say, okay, well, alpha prime of t, right, is equal to, well, the length, let me get straight to the point here. The length of alpha prime of t, what's that? Well, that's the square root of 1 plus 4t squared plus 9t to the fourth, right? So I can define s of t based at 0 to be the integral from 0 to t of the square root of 1 plus 4u squared plus 9u to the fourth du. That would be the arc length function. And so I can, I'm trying to figure out things straight here. Then the arc length function's increasing, so I can define an inverse function, right? I can solve, in principle, I can solve for t is equal to some other function. Oh, curses! I'm all backwards now. How to say this? Let's see here. So I want to say how do we make the curve alpha in terms of arc length? Well, I want to take this t and replace it with the, basically I want to solve this. Say solve for t equals to, let's say, h of s, right? Then, excuse me, we'd say beta is equal to alpha of h of s. Sorry, it's beta of s is the arc length parameterization of alpha. Again, I don't want to actually calculate that because I don't really care to do this integral. And even if to do that integral, I still have to solve for t as a function of s, right? So it's kind of nasty. But in principle, you can do this for some curves. In practice, many curves, you have to leave time or whatever your initial parameter is a parameter because the arc length is just simply incalculable. All right, so one last thing, and then I'll shut up for this part of the video. Excuse me. So, we have an important rule of calculus here, which is that proposition, I've called it proposition 1.4.7 in my notes, and it says that if you have a alpha, a parameterized smooth curve, and beta equals to alpha composed with h, a reparametrization of alpha by h, then beta prime of s is equal to dh ds times alpha prime of h of s. All right, and just to emphasize what's going on here, I should mention that this is an operator. This is an operator, right? Because we look at velocity as derivations, they're tangent vectors. And this guy right here is actually just a scalar function. Okay, so let's look at the proof of that. The proof of that actually shouldn't be totally unfamiliar. We have, so let's see here, the proof. We have alpha, well, beta of s, of course, is equal to alpha of h of s, right? So in particular, that tells me that the jth component of beta is equal to the jth component of alpha composed with h of s. So by the ordinary chain rule, when I differentiate that with respect to s, I do the derivative of the outside function, d alpha j, d alpha j, let's say d ds, right? It's kind of a bad notation, sorry. But the point is that that's evaluated at the inside function, h of s. I'll write that with a better notation just next here. and then times the derivative of the inside function dh ds. Now, typically I would denote that alpha j prime of h of s times dh ds. All right, and I can do that for j equals to, 1, 2, all the way out to n. And so what was our definition? Well, beta prime of s, remember, is the sum I equals, or let's say j equals 1 to n of beta j, well, d beta j ds partial x, well, deal with it. Partial x, go kill the bug then. Partial xj of beta of s. But that is equal to, don't touch it then, sum j equals 1 to n.
Try to smush it.
Well, stay away from it. Alpha j prime of h of s dh ds partial x sub j at beta of s. All right. Now, we have one of these terms for each j, so I can pull that out. And I have dh ds sum j equals 1 to n of alpha jth component differentiated, plug in h of s, and then I got partial xj. Beta of s is, after all, alpha of h of s. All right. But look at that. What is that? Well, that's nothing more than alpha prime at the point h of s. Just exactly that. So there you go. We have dh ds alpha prime of h of s. And that is what we set out to prove. Now, this proof really, you should keep in mind, I mean, basically this is just, if you had calculus 3 with me, I might have given you the same proof before, but instead of having this here, I would have written maybe x sub j hat, just for a unit vector in the jth direction, right? And then that would just been here and here and here, and and here. Well, kind of implicitly in there. So this is really something you should have seen before in calculus 3 anyway. But we've changed the notation on it. It's not much more than that, though, really. So in the next part of this lecture, we'll be talking about the push forward. I think I'm going to have to stop here for the moment, though, because the distractions are mounting. I think that's about all. I've got a few other examples in the notes you might want to look at, but I will pick up again here at the push forward or differential of the map. Thank you.